Greetings, my name is Jyoti Kodandapani. I am trainer and consultant in embedded wireless domain. You can get in touch with me using quatapa@gmail.com. In this presentation, I am going to talk about the real-time operating system. First of all, why operating system and why real-time operating system, what as functions, memory management, timers, and inter-process communication and interrupt management. What is real-time system? A system which operates in real time. Example, in a mobile phone, when you make a voice call, the voice is processed in real time, compressed, encoded, and sent over the air to the another mobile in the real time. Another example is the software running in the rocket. It has to do some real-time monitoring and controlling operation. A real-time system consists of processor, memory, plus some peripherals. It has external interfaces for the input and output. Example, in a cell phone, the external input can be your keypad inputs display, output can be audio. External interface can also be through your mic. This is a example real-time system. We have task, more than one task 1, 2, 3. We have a processor plus associated resources. Processor can be a DSP processor or a microprocessor or a microcontroller. Resources memory can be a analog to digital converter, digital analog converter, DMA controller. So the processor plus associated peripherals. And apart from this, there may be peripherals specific to the application. Example is in mobile phone you can rake receiver to receive a CDMA signal. So in between this hardware and task we have a real-time operating system. We have a single processor here but more than one task running. Somebody has to schedule the task one by one. So scheduling is one of the important functions of the operating system. The second important function is a memory management. See these task 1, 2, 3. Generally these tasks are not running all the time. Example, in a cell phone, a speech task that is running whenever you make a call. So instead of statically allocating memory to the speech processing, you can dynamically allocate a memory when the speech processing starts and release the memory when speech processing ends. So in that way, the same memory can be used by the other task also whenever they are running. So this memory management also is done by the operating system. These two are very important functions. The other is like a UI interface, user interface, file management. These things are normally is not supported in real-time operating system. This general purpose operating system like Windows, Linux, they provide all this UI interface, file management and a lot of other features. Even this embedded operating system like Android, Windows CE, Guru, they also provide all those interfaces. But real-time operating system, they mainly the scheduling, memory management. So why OS? I already told you, memory management and managing other peripherals, scheduling. It protects hardware from application. Application means task. I mean, a application can have more than one task. Why RTOS? is, as I said, is a real-time processing, preemptive scheduling. See, we saw in the system more than one task. There, you can assign priority to this task. So if a higher priority task wants to use the processor when lower priority task is running, it can preempt lower priority task and run. Higher priority task can run. Once higher priority task completes its function, then again control can return to the lower priority task. So preempt scheduling, more of hardware. It runs real-time operation runs more close to the hardware, specific to the hardware. So what is a thread or task? It is a functionally distinct entity. Example, speech task, data task, encoder, decoder. It is up to that software architect who designs the application to decide how many tasks you need for that application. What are the priorities to assign for each task? So you can combine many functions into a task or different functions for different tasks. It has to be done with the system timing analysis and other various scenarios based on various scenarios. Functions of the real-time operating system. So there are various states for each thread or task. Thread priorities, time slicing, preemption, scheduling. So each task have various state, internal state. I simply took example from one of the real-time operating system. Is once you create a task or thread, it goes to ready state. It can go to execution state when it start running, then it can complete. When it can go to suspended states. Example, when higher priority task comes, and from suspended state again it can come to ready state, then again start running. From execution state it can be terminated. So various operating systems are available in the market. They all have different state diagrams. So this is I took example from one of the operating systems. Thread priorities. Each thread can be assigned a priority. The priority assigned at the time of creation. So same priority can be assigned to more than one thread. Priority is assigned during the thread creation, and it can also be changed at the runtime. Pre-emption threshold. Generally what happens, preempting means when say let us say priority 1 up to priority 10. Priority 1 is the lowest, priority 10 is highest. And two tasks, priority 1 is running and priority 5 wants to run. Generally priority 5 is higher than priority 1, so it will preempt. But some OS you can put a threshold, like let us say preemption threshold is 6. So when priority 1 is running, 1 plus 6, 7. So the task with priority more than 7 only can preempt this currently running task. So this is preemption threshold. Some OS provides this function. Time slicing. Each thread is allowed to run only for a specific number of timer ticks. Timer ticks I will talk in the later. So you can specify this number of timer ticks at the time of the creation of the task or thread. Example, I want some task to be run for 5 milliseconds and basic timer tick is 1 millisecond. So at the time of creation you put 5 timer ticks. Scheduling. See, scheduling in the scheduler in the real-time operating system can check what are the ready tasks available periodically, let us say every 1 millisecond, or the scheduler can the scheduler can be activated whenever the task is ready. Priority based scheduling. Schedule the threads based on the priority. Okay. Priority, the tasks which are in ready state with higher priority can run first. First ready thread with the highest priority is executed first. Okay. If more threads of the same priority are ready at the same time, they are scheduled as per the first in, first out manner. So if more than, let us say, 5 threads of the same priority level, let us say 1, then the first thread which was ready will be run first, then second, like that, first in, first out manner. So as I already mentioned, higher priority thread can preempt the lower priority thread. Program control will be returned to the lower priority thread after completing the higher priority thread. Let's take this example. We have 3 tasks, priority 0, 2 and 5. 5 is the highest, 0 is the lowest. When the scheduler schedules, it is schedule priority 5 task first, then priority 2 task, then priority 0. You can also activate the task based on the events. When a ready task, suppose it is waiting for a event flag. So somebody else sets that event flag. So that task will get activated. Setting a event flag while a task is waiting for the same event flag. So the task is waiting for the event and somebody else is setting. So now the task waiting for the event will get activated. Similarly, putting a semaphore while task is waiting for the semaphore. Some task is waiting for the semaphore to get run, and other task is putting, then the task waiting for the semaphore will run. Round robin scheduling, here each task will get some amount of time. Then after all the tasks at the time, then again the first task will get time to run. Execution as per the first in, first out order. Next ready thread is executed after completing current ready thread. If you have 3 threads, let us say each task you assign 2 millisecond, 2 millisecond, 2 millisecond. Then after the last task completes, again first task will get 2 millisecond again. Context switch. This is very important functions parameter of the real-time operating system. Whenever you port a real-time operating system into your hardware, you will measure the context switch time. Generally, it is very fast in real-time operating system as compared to the general purpose operating system. See, here a lower priority task is running. At this point of time, higher priority task is ready. The control will be switched to the higher priority task. Now, after higher priority task complete, control again passed back to the lower priority task. Now, in this point, now the lower priority task, in order to run, it has to know previously where it was stopped. So before switching to the higher priority task, it saves the program counter, stack pointer, and the state of the various variables used in this task. Now while returning from this, it restores the program counter and the variables, all the register values, everything. So this time from switching from this state to the higher priority task, how much time it takes to save program counter, various register and variables. So that is one of the important criteria of the real-time operation. That is a overhead. How much overhead it consumes to switch from lower priority task to the higher priority task. Memory management. So here a memory block can be divided into sub-blocks of the same size or different size. See, generally, if you allocate a memory, the OS returns the memory blocks in the power up to, like the example, 64 bytes, 128 bytes, 256 bytes. If your application needs 100 bytes, even then it has to return 128 bytes. So whether you use 128 bytes or not, that will be returned. So when requested by the application, RTOS returns the starting address of the free memory block. So here these are fixed memory blocks. So here, so whether you use the complete block or not, it will return one block. So there are other memory management method where you can allocate variable memory blocks. Like task request 100 bytes, it will exactly return 100 bytes. So, but this kind of algorithm will take is more complex than the fixed memory blocks. Timers. See, generally the real-time system they have one or more hardware timers in the system, but there are many tasks are running. They all need some kind of software interrupt at certain in periods. So you have to derive software timers from a basic hardware timer clock. So this is a basic hardware timer clock. Let us say every 1 millisecond you add a timer. When you create a software timer, let us say for 2 milliseconds. So here you get for every 2 milliseconds, you will get a software timer interrupt. If you want to create for every 3 milliseconds, you can create. So you will get a software timer for every 3 milliseconds. In case of let's say speech processing task, I want the speech processing task activated for every 20 milliseconds. Okay. Then while creating a software timer, I can create for every 20 basic timer ticks I need time software timer interrupt for my task. Inter-process communication. The process here is a task, inter-task communication. These tasks can run on a single processor or on a different processor between the processors. Inter-process communication can be within one processor between two processors. This can be achieved using message queue, semaphore, event flag, and mutex. Here, there is a difference between mutex and semaphore. The mutex is slower than the semaphore. So mutex is nothing but a binary semaphore. So only one thread can own a mutex. More than one thread can get a semaphore by decrementing the semaphore on priority anywhere is available. Here it's not available. Event flags. Event flags is also one of the methods to communicate between the tasks. One task can set an event flag. The same more than one task can be waiting for the same event flag. Message queues. This is one of the IPC mechanism. Each queue can be used to communicate more than one message. This is an example in interprocess communication scenario. Here one processor, here one processor. So the task in the cell phone, let us say this processor 1 runs all the applications, and the processor 2 runs your GSM, GPRS, UMTS, LTE protocol stack plus DSP firmware, and there is a shared memory. This memory can be a one block or a group of flags. So this processor, it can write some data to the shared RAM and indicate through this inter-process communication. Let us say this shared memory blocks protected using a semaphore. It can indicate to the other processor using the semaphore, so that this processor can read the data and process. Priority inversion. When a lower priority task is holding some resource while which the higher priority thread needs, the lower priority that can temporarily assume the priority of the higher priority task. Let us say lower priority task running and it is holding a resource. So this it can the lower priority task can temporarily assume the. So see, if the priority, if you assign higher priority the lower priority task, then it can get the quickly get the processor time, and it can complete complete running. Then it can pass the control to the higher priority thread. Interrupt management. So interrupts can be disabled, enabled by the real-time operating system. Generally, the overhead to process interrupts is very less in the real-time operating system. So we need to measure the latency of the interrupt. The moment interrupt occurs on the external hardware pins and the time it takes to activate your task. This time is the interrupt latency. So this time will be very less in the real-time operating systems. Okay, that's all. Thanks for watching my presentation. If you need any queries, please get in touch with me using my email ID kotap@gmail.com. Thanks.